So we've got some content to get through. This slide covers all of our kind of big substitution reactions or useful substitution reactions. We've got a review of the reactions down below. Okay, most of those should, or all of those should ultimately be review or familiar. And it's those top 4 ones that are kind of new ones. Okay? We said they were new and interesting because what did they add to this? What do they add to our discussion? What's that? Stereochemistry. Okay, stereochemistry is now becoming a very important aspect of the reaction, and these reagents will focus on and allow us to be more specific. If we look at our example old ones down below, those are still stereocenters, but we didn't have the specificity to favor one over another. Okay, now we do. So we're going to start with our thionyl chloride just because it's an interesting one. It is one that typically you don't see in undergraduate labs because it reeks, but it does some kind of cool stuff. So if we take a look at SOCl2, we've got the drawing of the Lewis structure for it. What kind of chemistry do you see available to it? As a hint, it has nothing to do with what I just drew. What kind of chemistry do you see potentially happening for that thionyl chloride structure? Nothing. Okay, that's productive. Okay. If we go through and evaluate this, we have oxygen and 2 chlorines. Those 3 elements together are all what? What's that? Chlorines are halogens, the oxygen not so much.
They're electronegative.
They're all very electronegative. Okay, and because they are electronegative, what are they doing to that central sulfur? Making it extremely positive. So it has a large partial positive. Okay? To help us see that, we could draw out a resonance structure. And in drawing that out, hopefully we would see that we can form a positive charge on that sulfur. Okay? So that means our thionyl chloride will act as a nucleophile. No, not as a nucleophile, as an electrophile, particularly at the sulfur, which means what does the alcohol act as? What reacts with electrophiles? Nucleophiles. What is the alcohol going to act as? A nucleophile. Okay. Can understand a lot of panic about the exam coming up. These definitions of these terms is on the test. Okay? I think they are that important. I want you to know them. If you do not know them, you will get questions wrong that you should be getting right. They're there as kind of like gift questions where you don't have to worry about a whole bunch of other memorization of those reagents. Memorization of a reagent gets you one problem. Memorization of the definition of these terms can get you out to multiple, right? If not thousands. Right? So you do need to be able to have these definitions under your belt. After the nucleophilic attack, this now makes the oxygen what? Completely agree. It has now lost a pair of electrons into that bond, so it is now formally positive. Does oxygen want to be positive? No. So a variety of things can happen here. Typically what happens is first we eject the chloride because that is a good leaving group. That opens up our structure a little bit so that now that left chloride can act as a nucleophile, backside attack, and eject that sulfur oxygen chloride compound. That compound is inherently unstable and it will eject another chloride so that it can then go through and produce sulfur dioxide as a gas. That becomes really, really cool for a couple reasons. Okay? If it is a gas, what does it do? bubbles out of solution, which means the reaction becomes irreversible. Because it bubbles out of solution, it is a stable molecule. There's now a driving force to go through and make that, which means when I add thionyl chloride to the alcohol, it reacts very swiftly and efficiently. So we get a high efficiency reaction. Okay, so that's pretty cool for that reason. There's some people taking pictures. We'll pause for a second here. Okay. It is shown that we might also have to worry about that presence of pyridine. Okay. That presence of pyridine becomes kind of a big deal. Okay. In the presence of pyridine, we get the backside attack. Okay. Without pyridine, we get retention. And that seems kind of weird. Okay. So if we followed out our mechanism, we're getting SN2, some kind of cool chemistries. Every OH functionality will react with thionyl chloride. Are there other OH functionalities other than an alcohol?
Yes.
Yes, like
Carboxylic acid.
carboxylic acids. Are acids and alcohols different in chemistry? Yeah, pretty significantly, which is kind of cool that thionyl chloride is that reactive that it will react with both of them as if they are the same thing. Okay? So thionyl chloride will make a secondary appearance later on in the semester, in fact, third unit. Okay? The other part of this is this kind of cool chemistry. Notice that this mechanism being shown down here is a little bit different than the one shown up there. Anybody tell what's different about that? Especially the top one doesn't have arrows. I already had the chloride drawn. What is different about these two?
Where the chloride is attached.
Where the chloride is attached, what do you mean?
It's not on the backside.
In the top case, it looks like we've done a backside attack. In the bottom case, it looks like it's coming in and replacing at the exact same location. That is all dependent on the presence of pyridine. Okay? So if you change the solvent away from pyridine, you get retention of stereochemistry. If you use pyridine as a solvent, okay, you get inversion of stereochemistry. Why? Has to do with what pyridine can do. Okay? Pyridine is that benzene-looking structure with a nitrogen. It has that lone pair of electrons on nitrogen, which means that lone pair can act as a nucleophile. Was there, say, a strongly electrophilic structure in the presence or in that solution? Yeah, the sulfur was there. That pyridine can do a substitution in that case and sterically hinder the structure. Once it is now sterically hindered, chloride only has one option, backside attack. Okay? So it is the pyridine acting as a pseudonucleophile to go through and block that system out. Okay? So that is kind of a neat system behind this. So with pyridine, we get inversion of stereochemistry. You get rid of the pyridine, you get retention. Okay? It's kind of a neat question in that respect because we can use the exact same reagent and get two different stereochemical results. Okay? Which one should we memorize? What you need to memorize is the presence of pyridine or not. Okay? Because I have seen it show up in both ways. This is one that I've got flagged internally to make sure that if it shows up on a common final, okay, say like the ACS, that they're approaching the pyridine system correctly. Okay? Because it is a very subtle nuance. I've seen it presented incorrectly in multiple textbooks. Okay? So just be aware of that. The pyridine can make a pretty big shift in the end result. Okay? Watch for it. Phosphorus activation, pretty much the same kind of thing. What do we see that's special about our phosphorus-containing compound? What's that?
There's a partial positive on phosphorus.
Why is phosphorus partially positive?
The bromine is very negative.
The bromines are very electronegative, all withdrawing electron density from that phosphorus. That makes that phosphorus susceptible to nucleophilic attack. And what kind of a reaction? Okay. Or an addition reaction, define it.
Oh, wait.
No, too late. You got to define it.
An addition reaction is the addition of a pi bond.
Addition to a pi bond, which means what you would see is the loss of a pi bond through the course of the reaction. There's no pi bond here, which means not addition. Okay? What did change?
You added something.
Use of the word adding becomes dangerous again. Okay? We attached. Okay? How did we attach? Okay? Where did we attach? What did we attach? I heard an oxygen, or rather I saw it mouthed. That's good.
Oxygen attacked the phosphorus and
How did that bond form? What had to happen?
oxygen gave us electrons.
The oxygen shared the electrons. Phenomenal. Use chemistry terms. That is a chemistry term. It's going to be an inappropriate use of it as far as the mechanism. So coordination's not going to work. What did the oxygen have to do? Share electrons, which means the oxygen acted as it was a nucleophile. What did the phosphorus tribromide act as? An electrophile. Okay. So the nucleophile shared electrons with the phosphorus. Is that all that happened? Because if that's all that happened, then Lee's right. It's a coordination mechanism.
No, it ejected the bromine.
We also lost a leaving group. We ejected the bromine. Okay. So this sounds an awful lot like a substitution reaction. What did our phosphorus tribromide act as? And don't tell me electrophile, it's right, but we should have another term.
This is the substrate.
Anybody have any problems calling it a substrate? Does that fit the pattern of what a substrate should do?
No,
Why not?
because it doesn't have any carbons in it.
We're typically looking at our substrates as having carbon. Do they have to? No. Okay. The substrate is what is receiving electrons from our nucleophile. It is also the place that our leaving group is leaving. Done. It matches the bill. Right? Our substrates can apply out to larger reactions. When we talk about nucleophile, electrophile, substitution, all of those terms can be applied outside of organic chemistry. That's the part that's useful. The part that isn't useful is memorizing phosphorus tribromide, because you'll probably never see it, not in this class or outside of this class. So that becomes not as useful. Does that make sense? Okay? So when you're looking at these reactions, try to find the patterns and how they work and why they are working. That is going to help you on an exam. The raw memorization of reagents can help, but you will probably find it's not going to help as much. Okay? Feel free to prove me wrong. Okay? What is special now about our oxygen after that substitution reaction?
It's positive.
It's positive. Does oxygen want to be positive? No. What do we have? A great leaving group. It is also a very large leaving group, which means the bromide now has to come in from the backside to do our official substitution. Okay, and our official substitution, the substitution that we would want to do for this class, because that substitution is happening at
The same time.
a carbon. Okay? Starting to see where we're trying to push those reactions. It's the patterns behind these that you need to be following. Patterns take longer to work with. Okay? That is a challenging thing for students to recognize. We have to deal with a long game in trying to understand what's happening here. If you're not interested in the long game, you've got to memorize, and there's not a lot I can help you with. Okay? What type of reaction did we do? This was a substitution reaction. We look at our reactants to our products. What changed? We just did a substitution. We lost a leaving group. We gained a new atom. Okay? The end result is that we converted an alcohol to an alkyl halide. Cool. Substitution. What kind of mechanism? This is a bit of a dick question, just so you know. What do you got? Ooh, way to dodge the bullet on that one. Back-to-back SN2 reactions. It's two mechanisms. It's not one. We had to do two independent mechanistic steps. How do we know that?
Because you got you have an intermediate.
There's two arrows. That's it? Yeah, that's it. Look for the easy information to help you tip that off. Okay? So we know we have two back-to-back mechanisms. How do we know they were SN2? Well, the last one's a little bit easier because that fits in our carbon backbone, okay, our standard wheelhouse. We have a solid leaving group coming in doing a backside attack. That first one was a bit trickier. We had to evaluate how that reaction occurred. That meant pulling out the curved arrows to say, well, that attacks, that leaves. We're forming a bond, breaking a bond at the exact same instant. Those bonds are all sigma bonds, which means this is a substitution. Since it all happened at the same instant, that is also an SN2. So it's back-to-back SN2 reactions. Okay? What is a repercussion of SN2 reactions? Stereochemistry comes into play. The word that you should associate with an SN2 reaction is backside attack. If these pieces are there and you start to call backwards towards that knowledge from first semester, that can help you progress forwards. If that information isn't there, you have to memorize all of this as a new piece of information in 48 hours. Okay? Just like thionyl chloride, the phosphorus tribromide is so reactive as an electrophile, it will also work with carboxylic acids. Okay? Those two reagents are going to show up again in Unit 3 because they're the only way we can get to our most reactive carbonyl species. Okay? And we'll see those come back. Okay? Thionyl chloride plays a larger role there. The last one on that little slide summary was our tosylate. Okay? And you saw it as a TS. The TS is the standard abbreviation for tosyl, which is the structure shown. That squiggly is what's going to define that chemistry. Okay? If we make that squiggly an OH, what did I just make?
Alcohol.
We could reference it as a tosyl alcohol. That's not going to work because while that is an alcohol-ish, that is a carbonyl. And I've put a carbonyl right next to an alcohol. It's no longer an alcohol. Those two functional groups interact with each other. No way. That doesn't happen. What do we have? A functional group. Alcohol. Yeah, that's not going to work as well as I wanted it. Oh, well. What do we have?
Ketone.
Okay. A little bit borderline to call it a ketone, but I understand where you're going with it. Right idea. If we bring a ketone near an alcohol, can we call this a ketone and an alcohol anymore?
Carboxylic acid.
Now it's a carboxylic acid. Simple functional groups, when put near each other, can affect each other and change the reactivity. This is not a tosyl alcohol because it's not an alcohol. Okay? That OH is too close to the carbonyl-ish group there to be called a tosyl alcohol. What does it start to look like? Pseudo hint was kind of drawn down below. Almost perfectly color-coded. Okay? It's a tosyl group, except the functional or reactivity is now like an acid. This is toluene sulfonic acid. Okay? The name breaks down a little bit. We can't refer to it as just an acid because it's not carbon, it's sulfur, and that's where the sulfonic acid comes into play. Okay, believe it or not, you've seen the reactivity of this structure before. What does H2SO4 act as? Strong acid. H2SO4 is the exact same as toluene sulfonic acid. Except with another OH. So why would I choose toluene sulfonic acid over sulfuric acid? And as a hint, their reactivity is about the same. They're both very strong acids.
Well, it's got two hydrogens, one only has one.
So we could reference the amount of hydrogens there. That second hydrogen is almost irrelevant because the first hydrogen is so acidic. The second one doesn't really do much. So if it doesn't really do much, then is that explaining the difference between why I would use one or the other? Not really. What is there for the toluene sulfonic acid? Okay, a bunch of carbons, right? What would that do to the overall molecule?
Make it more nonpolar.
That would make it more nonpolar. If we looked at sulfuric acid, it is pretty much as polar as we can possibly get, right? Okay, fully protic. Why does that become a big deal? What do we react in organic chemistry?
Carbon compounds.
Carbon compounds. What are their solubilities in fully protic environments? Not very soluble, which means adding sulfuric acid to most of our organic reactions is not a useful thing because it's not going to mix with the organic materials. So what do I need? I need an acid that is soluble in organic solvents. How do I do that? Attach toluene to the end of it. We now have an acid that is organic soluble. Okay? What if we get rid of the squiggle and we replace it with a chlorine? Now what happens?
Same-ish.
What?
Same thing.
Same thing as
The last one. Just a little bit stronger.
as PBr3? Oh, you're saying the same thing as toluene sulfonic acid.
Yeah.
Okay. Would I expect with the chloride there to act as an acid?
No.
I don't have an acidic hydrogen anymore, so the chemistry changes a little bit. Okay. I kind of like the idea of the same thing, but then PBr3 doesn't make any sense because, right? But maybe something like thionyl chloride? How did the thionyl chloride react?
As a nucleophile, electrophile.
It acted as an electron acceptor. 3 electronegative elements, all withdrawing electrons from the sulfur. What do we have up here with our tosyl chloride? 3 electronegative elements, all withdrawing electrons from our sulfur. What happens to the sulfur? It's now a very good positive. It becomes electrophilic. Remember, we were talking about what happens with oxygen as a nucleophile. Okay? That would exceed the octet for sulfur by a lot. So what has to happen? We could break a bond. We could talk about breaking the pi bond, or we could talk about ejecting the chloride. Why is that the better move?
It's a better move.
Chloride is more stable than a negative oxygen. What's the result? Does the oxygen want to be positive?
No.
No, it's actually quite acidic. Anything remotely basic in solution, for instance, the starting alcohol can remove that hydrogen, and we would now end up with OTS. What happened to the arrangement of atoms around that center carbon?
Nothing.
Nothing. Why?
Because you weren't making the substitution at that carbon.
Where did all the chemistry occur?
At the sulfur.
At the sulfur and at the oxygen. It had nothing to do with the carbon. So there is no change in stereochemistry. It doesn't make sense to refer to this as retention or, by the retention or inversion terms, because there's no chemistry happening there. Does that make sense? But what this does do is it creates this OTS. Okay? Why is that potentially useful? Why was sulfuric acid such a strong acid?
Because it's so polar.
Oof. Let's try that again. Whoop. Why is sulfuric acid such a strong acid?
Because it ionizes completely.
Why would it ionize completely? Yes.
Because it's such a stable, you have such a stable leaving group. And
It is
it's
exceptionally stable. Bromide's a great leaving group. Why?
Stable.
It's stable. Chloride's a great leaving group. Why?
Stable.
Stable. Hydroxide's a horrible leaving group. Why? Unstable. Water's a great leaving group because stable. Sulfate is a strong acid because it generates an exceptionally stable negatively charged structure. What did we say was the relationship between our sulfate and our toluene sulfate? They were
pretty much the same.
pretty much the same, which means that OTS now is a great leaving group. That great leaving group can be kicked off by virtually any nucleophile. In what kind of a mechanism? SN2. There's where the inversion of stereochemistry happens with the tosyl leaving group. Okay? So this becomes one of the challenging things within this is you'll go through to try and memorize reagents without understanding why, and you'll start falsely associating stereochemical associations or creating false stereochemical associations. Recognize what the chemistry is behind them. That will help you process through these better and more effectively. Kinda, sorta? Okay. Kind of feel like that jumped. Did that jump? No, it didn't. Okay. Ether synthesis. If I want to make an ether, what do I want to do? If I was to turn that structure into an ether, let's even simplify it. How do I make an ether? Guys, let's try it this way. Identify an ether functional group.
C, double O.
Is that an ether functional group? No, what is that?
C.
Carbonyl is the best answer for that. If we specify that those are carbons, it's now a ketone. If we make that an OH, it's now a carboxylic acid. If we make that an H, that's now an aldehyde. If we make that an OC, it's now an ester. Okay? So the carbon-oxygen double bond is a very versatile functional group as a class. Calling it by the substituent name becomes challenging. It's a carbonyl. Okay? I asked for an ether. Carbon, good. Oxygen, carbon. There's an ether. Okay. If we go through and look at the starting material that I've got, well, there's a carbon. There's an oxygen, right? That looks like what I started with. Minimally, what do I need to add? Should probably use a green box. In that green box,
CH3Cl.
I need a carbon. Okay. I like that you filled it out with a CH3. I didn't specify that, but let's make it easier. A CH3. You then said you want a chloride. That's a pretty big jump. I've only got one carbon there. How do you know chloride?
Intuition.
Well, work through that intuition. Prove your intuition right.
Because OH is a bad leaving group.
Okay.
So I thought of a good leaving group.
Okay, and by that token, that oxygen then, you're talking about when running this reaction, you're talking about making the orange bond, right? What charge would the oxygen most likely be in making that orange bond? Okay, let's call it a positive. Would I expect oxygen to be positive? No, why not?
It's very electronegative.
Oxygen is the second most electronegative element on the periodic table, meaning what is it doing with electrons? It's hoarding them. Okay? The most likely charge for that oxygen is not going to be positive, but negative. And before we go, oh man, positive was wrong, that was horrible. No, it was absolutely fantastic, because now that we had an answer, what could we do? We could reason through it. What's fantastic about watching this is we just talked about how important it is to write this down. One person has a pencil in their hand.
Wait, I think I have an answer.
Okay? We aren't even on that yet. Okay? Do you get where I'm going with this? You need to be thinking and writing these processes to be able to work your way through it. If you aren't writing them down, you're trying to keep it in your head. Guess when that positive oxygen is going to show up? At the exact wrong instant, which will be Wednesday. Okay? And that's going to suck. You need to be addressing this drawing attitude behind how we work through these things before you get to the exam. Oxygen is most likely negative, which means what does the carbon have to bring to this party to get that orange bond?
Positive.
It has to be positive. Because if it was negative, what would happen?
They would fight each other.
Negative to negative, we get repulsion. They don't interact. So the carbon, fantastic. I love that we've got that answer there. You've elaborated and gave me a CH3 just to fill it out. That's fantastic. You then threw in the chloride. Why'd you throw in the chloride?
It was just bad intuition.
You're good.
What is the characteristic of that chloride? I think I heard it. Well, why would chlorine leave? It's a good leaving group because it is stable. It's more electronegative than the carbon. It's larger than the carbon.
So it's going to charge.
So as it leaves, it takes the electrons with it, making the carbon
Positive.
positive. What charge did you want that carbon to be?
Positive. But
What-
you need something else.
Do you have that positive carbon?
Yeah.
Yeah. Is that a good reagent?
Yeah.
Yeah. That's a really good reagent. Okay? But you need something else. Why do you need something else?
To get the oxygen to be negative.
We would want the oxygen to be formally negative. It is only partially negative now, okay, because it has those lone pairs. Okay? It has a hydrogen on there. That hydrogen is weakening that negative characteristic, making it less.
Electronegative.
No, it won't change its electronegativity. Making it less. It's actually making it more stable.
Less likely to leave.
Less reactive. It's making it less nucleophilic. If the oxygen is negative, what must it do? Share the electrons with the carbon as a nucleophile, because it is now sharing those electrons. Okay? And you're right, that hydrogen is problematic. I would have to somehow get rid of that hydrogen. I don't want the hydrogen on there.
Chlorine is strong enough to pull it off.
Chlorine will not remove the hydrogen.
NaOH.
Okay? That absolutely won't be the case, because then you would form
HCl.
HCl, which is a strong acid, so that's not going to happen. Okay? So what could we do to make that oxygen more willing to attack that carbon? I need to get rid of the hydrogen, right? Okay? So now let's take a look at that bond, that OH bond. Okay, where would I expect those electrons to go?
Oxygen.
Why would they go to the oxygen?
More electronegative.
Oh, it's more electronegative. Fantastic. Which means the hydrogen would become what charge?
Positive.
Positive. What would I need to stabilize that positive hydrogen?
OH minus.
I would need maybe an OH minus.
Oh, so you have water in it too. Actually, wait, no, you don't.
What kind of reaction should I run first? I need to run an acid-base reaction first. That acid-base reaction is going to get me my CH3O negative. That can now attack my partially positive carbon. Okay? Is OH a good choice? If OH is in solution, what can it act as? A nucleophile. Is there anything electrophilic floating around like a partially positive carbon? Yep. Which means if I add the OH minus, it could do a substitution instead of my alcohol. Is that going to get me the same ether product? No. So I want to add a base that does not react in such a way that it could act as a nucleophile. Is there a non-nucleophilic base?
There is.
Yes. We've talked about 2 of them. 3 of them. I guess the longer we wait, the more I can think of them. All I've really got is 3. NaH. Sodium hydride is a non-nucleophilic base. Okay, it can remove that hydrogen. That would work. What else could we use? T-butoxide. I'm not even going to bother to draw out the structure, and I'm going to spell it the abbreviation wrong. DBN or DBU, one of those 2. Okay, also non-nucleophilic bases. The 2 ones that you should absolutely know would be your T-butoxide and your sodium hydride. Those are huge. Okay? Less common, but sometimes just as trickily thrown in there. Sodium ion. What is sodium ion going to do? Well, nothing. That's why I didn't add sodium ion. What is that?
Solid sodium.
Solid sodium. Solid sodium will react and remove hydrogens. Okay? As a strict acid-base reaction.
No.
Enough. Okay? So we don't have to worry about the sodium doing any nucleophilic attacks.
Is it an acid base?
It ends with an acid-base reaction.
Okay.
It's a little bit more complicated than that.
You're just essentially doing the
It acid-based. Memorize it as a non-nucleophilic base. Okay? And we've now done an ether synthesis. The synthesis you just came up with on your own, in theory you read about it, but maybe you didn't, is a Williamson ether. Okay? That process was making a good nucleophile. Okay? We made the nucleophile better so that it could react. Could we have also made a good leaving group? Yeah. We could do that by turning the alcohol into a good leaving group, by, say, adding an acid. The problem with that, you're only going to get symmetric ethers. Okay? If we want an asymmetric ether, we have to go through the Williamson. Okay? So we do a strong base, make that strong nucleophile, react it, we get our ether. Okay? So let's take a look at 2 reactions here, okay, which gets us towards synthesis. We've already started talking about synthesis, believe it or not. Which one do you want to take a look at? Left or right? Left it is. If we're going to look at that ether, we need to decide which bond is the bond that we're going to make. That could be a hard question. Should I be making this bond? I see you, Mustafa.
No,
Why not?
because that's not the bond I'll make to ether.
I just need to end with this ether structure. It does not necessarily mean that the process of making my product has to result in the formation of the ether. Okay? For instance, is it possible that I split it like this and then do a CH3? If I can get these two to react, wouldn't I have my ether?
Yeah.
But didn't you have it?
Yeah, I would. I did have an ether. Did I have the ether? No. Right?
That's also a massive
So
reaction.
if I could get those two to react, I do achieve this. So what we're asking is that a good step to try and do? Why not? Why is that bond hard to go through and make?
Because the CH3 is stable, and the other carbons are stable.
To get a bond to form, what do I need? I need electrons. One of these species needs to have electrons. Which one do I want to make it be, top or bottom? Bottom it is. Top one's going to be positive. Okay. Can I get a negative carbon? Very few reagents allow us to get negative carbons. Why?
It's not very stable.
Why is it not very stable? Yes. It's small and it is not very electronegative. The generation of negative carbons is such a challenging thing to do that virtually all negative carbon reactions are named reactions. Someone got to attach their name to it. Grignard, Gilman, Robinson, Claisen, Aldol. Aldol is not a named one, but whatever. Okay? So negative carbons are not easy, which means synthetically not a good option for us to try and do because that's going to be expensive. Which bond should we look at then? Why the CO?
We need the chemical side. Follow negative charge.
Okay. If I look at that bond, if I was to break that bond and split it into the two pieces, where do the electrons come from to make that connection? Well, again, if we think about this as our negative-positive reactions, one of those atoms needs to come in as a negative. Which atom might that be? Why?
It's more stable.
Why would oxygen be a good negative? It is more electronegative. It would stabilize a negative charge, which would then mean I'd need a carbocation at the other end. So when we look at a synthesis and we're told make this compound, we need to look at that structure and we need to find the easiest places to break it. Where are the easiest places to break?
Right there.
In general, the more polar bonds. That's it. Look for your most polar bonds. That's where it reacts. That's where you get differences in electronegativity. So you can find a negative, which would mean it would act as
Nucleophile.
a nucleophile or a base. I'd find a positive. It would act as an electrophile or an acid. It's zeroing in on those aspects that allow us to progress through synthesis. It's not just, ta-da, I know the answer. You have to start carefully breaking apart these structures for synthesis, and that becomes challenging. Okay? Why does it become challenging? Okay? Another suggestion was thrown out there. We need to break the carbon-oxygen bond, right? Was the red one the only carbon-oxygen bond? No, there was another one over here, which means
You could have broken the other one.
which synthesis is now more correct?
Neither.
How would we know? We would have to go through and say, well, I'm just going to say it is and just see what happens. What would these things do? How would they react? Okay? So we're hearing an argument for stabilizing a carbocation. A tertiary carbocation is really nice. Primary is not so great. Okay? That's assuming your reaction runs in what kind of a mechanism? SN1. Does it have to run SN1? No. And in fact, if doing a synthesis, we tend to avoid SN1 because
Stereochemistry.
multiple products come out of that. Okay? So I like where you're thinking, but we have to push it beyond just, positive charges are more stable there. We have to evaluate each of those stages. Okay? So let's push this backwards further. Where could I get that negative oxygen? Okay? That red lone pair had to come from somewhere to make that negative. Where did it come from? Whoops, and that's not an H, that's a CH3.
Probably an H.
Probably an H. So to go this direction, what would I add?
Base.
Okay. Notice we have a new arrow in here, that weird kind of double line with the little greater than, less than, whatever symbol that is. That is known as a retrosynthesis arrow. We are thinking backwards. To get the structure on the left, I need these pieces. To get these pieces, I go further back. Okay? So cool, that ends at a place that's reasonable. How about to get that piece? Because I can't throw a positively charged structure into this. I would need a leaving group. Name a leaving group. Chlorine. Awesome. I've now identified pieces. I can take methanol, react it with a base to make my active negatively charged species. I can take and then add my tertiary chloride into that system to try and get that product. That's a strong nucleophile because it's negatively charged. Suggest which mechanism? SN2. What kind of substrate is that? Tertiary. Do tertiary substrates work well in SN2? Ouch. Okay. Strong nucleophile and also strong base. Do tertiary halides work well in E2 mechanisms? Yes. This reagent pathway does not take me to the ether. It instead takes me to the alkene. By drawing out these steps and then saying, well, now these are my pieces, I can work forwards, if you will, to evaluate if that's a good option. That was a pretty bad option. What about the other result? Where could I get the negative oxygen from? Tert butanol. How would I get it back to the negative oxygen?
Base.
Or strong base. Where do I get the halide from? Or sorry, as I give away that answer, let's just draw it now.
Methyl halide.
And people may have been saying for the bottom one, I don't like the bottom one because that negatively charged species would act as a base. Where's the acidic hydrogen? There isn't one. No acidic hydrogen means
No base.
it can only act as a nucleophile. It's now going to do a strong backside attack. Why is it going to do a backside attack? It's negatively charged, making it strong. Is the substrate capable for a backside attack? It's as least sterically hindered as we can get. We had 2 answer choices. Only one of them works. How would you know? You have to write them out. We've taken a step forward, by the way, because we're now beyond 1 pen and I see 3 pens, 4 pens. Okay? But it is that writing process and that walking through those reactions that you need to do. And if you aren't walking through those, you won't get to a satisfactory answer unless you've memorized the answer. Okay? Internal ethers, known as epoxides, okay? Or more generically, oxyranes. Okay? We've seen how to make an epoxide before. What could I add to the alkene? Yep, that's right. That string of letters, MCPBA. Metachloroperoxybenzoic acid. Any kind of peroxy acid is going to trigger that, but the metachloro tends to be the most common one shown. Okay? Is there another way to go through and do it? Yeah, well, we just showed that we could go through and make that linkage without doing some weird peroxy stuff. So what we can do is start with our alkene and we could add bromine. Okay, that forms the bromonium ion. If we do it in the presence of water, water will act as the nucleophile instead of the bromine as long as water is in high enough concentration. The result? We get the alcohol and the bromine connected. Bromine belongs to which group? Halogens. This is a halohydrin structure. So you can form an epoxide through a halohydrin. How? Well, you add a strong base. What's the base going to do?
Rip off the hydrogen.
Remove the hydrogen. As long as the oxygen and the leaving group are on opposite sides of the ring, backside attack, we kick it off, we get our epoxide. Okay? How many epoxides would we get in this synthesis? It's kind of a mean question because I think with this structure you only get one. There are two possible epoxides that come out of it because you get the top epoxide versus the bottom epoxide. Okay? So there's two possibilities. Because this one is symmetric, we only see one. Okay? Why would we choose to go through this method versus, say, MCPBA? Do you think one is better than the other? Let's try that.
How toxic is MCPBA?
Meh.
How expensive is it?
It's probably less toxic and less expensive than bromine. It's a guess. The top synthesis requires 2 steps. The bottom synthesis requires 1 step. Okay? The top synthesis is going to require using more reagents than the bottom synthesis, which means the top synthesis is going to generate more waste and more safety issues, which means the top synthesis is bad. The bottom synthesis is a little bit better because it minimizes some of those chemicals. Okay? To that same end, we've decided to classify that type of a reaction, less chemicals, by a name. We call it green chemistry because we're thinking about the environment. It's a nice billing, but that is totally not at all what green chemistry is about. Green chemistry is about minimizing safety repercussions because safety repercussions are expensive. Okay? It's a dollar amount. That's what drives green chemistry. Okay? So, epoxides formed with reactions with alkenes. Okay? In that, we get 2 possible products. Okay? So this one actually shows that. That kind of sucks. Okay? Don't stress about this one. But if we get 2 possible products, that's generally when people go like, I don't want to do that again. I need only 1 product. So what does somebody do? Spend their life trying to change the reaction conditions to get what to happen? 1 product. This was done by, I believe, a man with the last name of Sharpless, but I honestly don't know whether he's male or female. Okay? This combination of reagents, you add your titanium tetraisopropoxide and DEET, plus or minus. And what those will do is force one epoxide over the other. Okay? That's kind of neat. That's all I want you to know. We can cause reactions to do one thing if we want them to. Okay? But it usually requires a little bit of extra work and more reagents that we don't want to bother memorizing. Okay? So, reactions of epoxides. Under basic or neutral conditions, we have to use a strong nucleophile. Why? If we're under neutral conditions, we need to evaluate the leaving group ability. Okay? There are 3 bonds in the epoxide. Which of those 3 bonds is least likely to break? Red, green, or blue? Blue. Why? Because the book didn't show that one. Do better. What's that?
Uncharged.
I don't know what uncharged is referencing.
Wait.
The oxygen is more electronegative than the carbons, which is doing what to the red and green bonds?
Weakening them.
Weakening them. It polarizes them. The blue one in between, both with carbons, that bond is now relatively strong. So we can ignore that one. We're now dealing with red and green. To break either of those, the oxygen must steal the electrons. Why should the oxygen steal the electrons and not the carbon?
Because oxygen is more electronegative.
Oxygen is more electronegative than the individual carbons. So it goes back to the same principles we've been referencing. Okay? So now the question becomes, which one? Does the nucleophile attack there, or does it attack over there? Okay. This is all going to come back to evaluating the structure of the reaction. Do you have a good leaving group? Okay. If that bond, let's just pick the green one just for giggles. If that bond broke, we would have a negatively charged oxygen. Kind of like hydroxide. Does hydroxide pass the normal face test? No. That would be very, very painful. That is a horrible leaving group. Okay? If we do the red bond, we see that we'll get the same result. A horrible leaving group. Okay? So it must be forced off. To be forced to form, the nucleophile has to be an even worse performing face test than the oxygen. I have to have a stronger nucleophile than a negative oxygen.
Fluorine.
Okay? I don't even care what it is. Okay? But I have a negative nucleophile. If it is a strong nucleophile, that would suggest SN2. And if it is SN2, which substrate do I want?
The least.
I want the least sterically hindered, which means the less substituted position, green is less substituted than the red, and I get the green result. Nothing changes to the stereochemistry at the other position. There's my nucleophile coming in. Is a negative oxygen a stable thing? No. So what do we do? Stabilize it with a hydrogen. So we would need to add an acid. I don't care what acid, let's just say H+. The oxygen comes in. The end result is that our nucleophile attacked the least sterically hindered position, and we have an alcohol now at the other position. Yeah? When did I add the acid? After. How would I signify that in my reaction? I need to show this as multiple steps. Step 1, nucleophile. Step 2, acid. These must be distinct steps. If they aren't distinct, I'm adding the acid at the exact same time, and what does the acid do? Neutralizes the nucleophile. The reaction doesn't go anywhere. Okay? So this is basic or neutral conditions. Okay? This is one of the reasons why it's important to look at the chemistry and evaluate what's going on, because what students will often do is now memorize, epoxides will react by least sterically hindered site. And then we switch the conditions. Uh-oh, did I just freeze it? Nope, I didn't yet. If we now switch to acidic conditions, the most reactive thing is now that H+. What happens? The epoxide oxygen attacks. What have I now formed?
Carbocation.
It is not a carbocation.
Positive oxygen.
A positive oxygen, which happens to be a
Unstable system.
phenomenal leaving group. The chemistry has now changed. No longer looking at a bad leaving group that needs to get forced off. I've got a leaving group that's already trying to break off. Given the choice, where would I want to break? Do I want to break the red or the green?
You want to break the green. No, sorry, red.
Why would I break the red?
Because you're going to end up with a carbocation if you break another one.
I would start to form a partial positive charge at the more stable position. That red bond starts to weaken a little bit more. Notice I'm not showing a carbocation form here because no carbocation forms. Okay? What is going to help that oxygen finally clear away from the structure? The nucleophile. Notice in this case what is different about the nucleophile. It's not charged, thereby making it a weak nucleophile. Which mechanism is favored by a weak nucleophile? SN1, which substrate? More substituted. The nucleophile attacks the more substituted position. The end result, if we draw out our structure, our oxygen is now at the less substituted position, and our nucleophile is at the most substituted. We get a different result. Guess what? For every single epoxide reaction in a multiple choice test, you will see this answer and the other one. Guaranteed. Okay. What other answers might you see? What is special about that blue bond? It is a sigma bond. And sigma bonds, as we all know, can freely rotate. They can draw the structure with a free rotation about that to entirely make it look whack-jobbed. Okay? What's another common answer that they could throw at you? Did the nucleophile still attack the most substituted position? In that red box? Yes, it did. What is different about this?
It's on the same side.
It's on the same side. Can that happen? If you know the mechanism, no, it cannot happen. If you don't know the mechanism and all you've memorized is that they add to more or less substituted, you also encounter problems. Okay, makes sense? So there's tons of ways the epoxide reaction can be made confusing. If you understand the chemistry behind it, becomes significantly easier. Where did most of that chemistry come from? We dropped a lot of terms. Substrate, backside attack, forming cations. Okay? Those are all terms associated with first semester. In which reaction? Substitution. If you apply the knowledge from first semester, second semester becomes easier. If you don't apply it, second semester becomes harder and infinitely more so. Okay? Which is what we talked about in the first week. Okay? There's our summary that puts it all on one slide so that if you wanted to go back and try and memorize right before the test, not a bad idea starting like Wednesday, just memorizing reagents. Okay? Which then gets us into synthesis. Okay? We're going to ignore the directions up at the top because those aren't a big deal. We've already been going through some of these kind of hint things at the bottom. Chapter 13 is synthesis. It's not new content. It's an entire chapter that just spends its time going backwards and says, well, you remember this reaction? Use it. You remember this reaction? Use it. Okay? And it's a question of how you string together pieces. Okay? That stringing together is a sequence of questions. Anybody notice as we go through lectures that I ask a lot of questions? Yeah, how many people write down those questions? Yeah. Guess what you need to do on a test? Ask those questions. Okay? The overarching question is almost always virtually impossible to guess outright. You need to ask simpler questions. What is lecture all about? Simpler questions. If you can't answer the simpler questions, that makes the harder questions a lot more challenging and ultimately just memorization. So with synthesis, you need to look at your structures, beginning and end. Okay? What position is the chemistry within your final and starting structure? Has it moved locations? Does this look vaguely familiar?
Yes.
Guess what that was? A synthesis. Where's the chemistry in your starting structure?
Tertiary bromide. Tertiary bromine.
That bond is where the chemistry is located. Right? Probably most important would be to identify the carbon. Because what's the bromine going to do? Leave and never come back. So we don't really care about that. But we can identify where there's chemistry. We do the same thing with the product. Where's there chemistry in the product? Well, where the oxygen is located. Does the chemistry appear to have moved? Yes. To move, it's going to have to go through different reactions. So the question is, how do we get it to move? Well, that would require that we know what our reactions are, which would be substitution, addition, elimination, acid base, radical. In any of those, can we get the chemistry to jump positions like that?
Yes.
Really? Which one does that?
Substitution and addition.
Substitution and addition. So let's start with addition, the easy one. What is an addition? Adding what? Adding to a pi bond. Do I have a pi bond? No. So addition's not right. Substitution. Where does substitution occur? Where there's a leaving group. Fantastic. I have a leaving group. Now where does the chemistry? Stays right there at that exact same carbon. Did it move? No. Does substitution or addition work? No. Does radical work? It's not yes. No. Do any of the 5 single reactions work? No, which means multiple steps. We need to get the chemistry to move positions. If I look at a substitution, most substitution reactions, there are some exceptions with rearrangements, okay? The chemistry stays at one spot. Okay? In addition, what happens in addition? I have 2 carbons of a pi bond that can react, 2 positions that are reactive. I'm not starting with 2 positions reactive. I only have 1, so addition's out. Okay? Radical, it's not an alkane or an alkene, so that doesn't really fit there. Acid base, it's not acid base because it's not acidic, which means elimination. The end of an elimination, I formed a pi bond. A pi bond has 2 reactive sites. I'm starting with 1. If I do an elimination reaction out of the gate, has the chemistry moved positions? Yes. I now know that one of my first steps should be an elimination reaction. Right? Not just, I'm going to throw some stuff at it and hope it works. You have to know those pieces and those processes to think through them. You're finding that chemistry. After we found the chemistry, what did I ask you guys? Which reaction type completes it? Okay? If it doesn't complete it, now I've got to decide what things can I do. Okay? Atoms or elements that are missing. Okay? In the course of the reaction, I get rid of the bromine. Bromine's a good leaving group. It never comes back. Probably not a big deal. Where the hell did OH come from? Did I start with it? No, which means somewhere through the course of the reaction, I need to see an OH coming in. Okay? By identifying these pieces, you can now come up with a predicted synthesis process. It requires practice because you also have to know the reagents. Okay? But just knowing the reagents won't help you because a reagent gets you one step. Synthesis, by definition, is more than one step. Okay, make sense? So when I talk about knowing how to fit pieces together, this is why you have to be able to fit larger pieces together to see where those reactions are happening. This one becomes easier. Why is this one an easier thing to do? I'll give you all the reagents, you just have to do it. Okay? But even this one, if you've only memorized reagents, it becomes problematic. Why? Okay? The why is actually going to come from the observation I've now made multiple times in this class. What are you doing with your pencil? Nothing. Which means you do step one and you did it where? In your head. You then try and throw step two at it in your head. Then you got step three in your head. And guess what ended up happening? You just vomit all over the papers. Potentially, literally. Okay? Synthesis is a relatively small part of this exam. Okay? So don't completely freak out when you see it. You can just accept that you're not going to get those points. But remember, there's lots of places where we can make that exception. Just be like, I'm just not going to get those. Okay? You have to decide somewhere where your pattern's going to be. Kind of make sense? Should we do it?
Yes.
Step one is what?
Your alkene attached to chloride.
The alkene is a source of electrons, which makes it a nucleophile, which means what do I have to find in the next piece? I have to find an electrophile. Is water a good electrophile? Okay. If water is an electrophile, there must be an atom that can accept electrons that is not hydrogen. Can the oxygen accept electrons?
Yes.
No.
Okay. The oxygen is not good at accepting electrons because
Has them.
1, 2, 3, 4, 5, 6, 7, 8. We call it an octet for a reason. The octet is full. Does it have a good leaving group? Because we can have full octets as long as there's a good leaving group.
No.
Is hydride a good leaving group? No. Is water your electrophile? No. So if we understand the chemistry, we can take a guess. Pfft, water. Whoop, failed. Well, if it's not water, it's got to be the chlorine. And that's where people go, oh, but chlorine always has electrons. Chloride does. This is not chloride, this is chlorine. Okay? Full octets. You'd be like, oh, Mike, you're just full of crap again. Do we have a good leaving group? Can chloride stabilize the charge? Yes. There's your leaving group, there's your electrophile. We can now run that reaction. What should we be forming in the process of that reaction? Okay, well, this would be an electrophile starting with a pi bond, which would mean electrophilic addition. And Mike went through and said, hey, there are two classes that we can run in. 3-membered rings or 4-membered rings, and it makes a big deal with the end result. What was that classification? Good leaving group means 3-membered ring. I need to be forming some kind of 3-membered ring. Well, I've got the 2 carbons, which means, oh God, a positive chlorine. Mike must be an idiot. That's horribly unstable. Absolutely. So what do we need to find? Something to stabilize it. That chlorine is going to steal electrons. And because it is a great leaving group, it wants to take electrons, we're going to break the more substituted position. Water is our nucleophile. Oh, water was there for a reason, can come in. Okay? All of those pieces, we're going to erase it all. That was 74 minutes for the record. If anybody wanted that. Our chlorine. Do we have stereocenters? Yep. Okay, backside attack. We add NaOH. What is NaOH? Strong base. Is there anything acidic in that structure?
Yes.
Yep. the hydrogen. Very next step, that just looks like a bunch of H's. If anything, those are positive H's. Why the hell did I add a base if all I'm going to do is add an acid?
Because you're going to put that.
Because I missed a step. Chlorine belongs to which group? And that would be this would be a halohydrin, followed by a strong base is the internal ether. We've got an epoxide. Now what happens? Do we have a strong nucleophile? To be strong, we must be negative. Okay? Not negative, which means we're looking at a weak nucleophile. The weak nucleophile is going to attack where? The more substituted position. Let's just say that was wedged. So the methyl will be wedged and then something else will be in here. What is that something else? Which of those species is our nucleophile? CH3OH or TSOH? Don't worry, we just did a lot of lecturing. Really don't blame you. TSOH. TSOH, acid. That's an acid catalyst. If it's the acid catalyst, what's our nucleophile? The CH3OH. Okay. I did a deprotonation and protonation at the same time on that, officially plus an enantiomer. Okay. I see some people going, God, that was crazy how fast and quickly he went through and did that. I knew the answer. Okay? So it isn't that impressive. Okay? But it's that thought process that you should be working through. If you're memorizing reagents, you should be able to draw the answer of each step and then take that and move forward. You don't have to draw out all the mechanistic pieces. Okay? Kinda. We have nitrogen acting as a nucleophile. Okay? As a nucleophile, you're absolutely responsible for that. Okay? You are not responsible for what happens after nitrogen acts as a nucleophile. Those that have read into Chapter 10, that is the Hoffman elimination. We also have enolates in Chapter 10. Okay? Believe it or not, we actually already talked about that. Okay? We just didn't go into the specifics of what we do once they are formed. That chemistry is kind of borderline. I think you should know it. Okay? And I phrased questions that did not dig into that aspect from Chapter 10. Okay? So the Hoffman elimination is off the test. Enolates as reagents is kind of borderline because we've addressed virtually 4 or 5 of the subsequent slides we've already talked about. Okay? And then the rest is just kind of there. Okay? Diels-Alder we didn't get a chance to talk about in class, which means I will probably count half of them as, well, actually no, because you were supposed to watch the answers on that. So officially we do have Diels-Alder. Okay? Exam is Wednesday. There's a lot. Total possible points for the exam is 114.